Good afternoon, everyone. Today I will be talking about anomalous chiral symmetry and the QCD phase diagram. I will start with the QCD phase diagram. So on the x-axis we have baryon chemical potential. On the y-axis we have temperature. And over here this different color represents the different phases of the QCD phase diagram. This blue color represents the state where quarks and gluons are confined, whereas this yellow region which you see, these are the deconfined state. Here the degree of freedoms are quark and gluons, and this yellow region which you see over here, this is the colored superconductor. And this solid black line over here is the first order phase transition line. And this black dot is our second order critical point. And this band-like structure or the fuzzy region over here is the smooth crossover transition. And for mu b is equal to 0, the smooth over transition is roughly around 155 MeV. This was the prediction given by the lattice QCD and later verified by this experiment LHC. Many of these experiments like LHC, RIC, NIC, and FAIR, these are trying to probe the different reason of this QCD phase diagram. So it will be interesting to look at the QCD phase diagram, so how it changes as a function of this quark masses. So in the chiral limit, by chiral limit I mean when the quark masses goes to 0. So here is another axis, this is the third axis. So you can see that as the quark masses goes to 0, this smooth over transition changes to a second order transition. So this red solid line represents the second order phase transition. And also this critical temperature changes to 132, which was earlier it was around 156. Okay, so we already know that in the 2+1 flavor QCD, the mass of up and down quarks are much less than the QCD scale, and due to which our U2L cross U2R symmetry is minimally broken, and the breaking of the non-singlet part happens to be around temperature 156 MeV. However, the UN part of the chiral symmetry is anomalous, and it can affect the order of the phase transition in the limit when mass of up and down quarks tends to 0. And it is not yet clear whether it is effectively restored along with the non-singlet part or not. So how we gonna study it? So one of the way to study these non-perturbative phenomena is through lattice QCD. So over here we basically discretize our theory on a discrete space and time, and we try to study it numerically. So here we study the eigenvalues spectrum of, in our work we basically study the eigenvalues spectrum of Dirac operator, which contains the valuable information about the fundamental properties of QCD. So, and we ask a question, does the non-singlet part and its singlet part get restored along the same temperature or not? And can we explain it in the terms of the eigenvalues? So here we work on a finite box with a small lattice spacing, and ultimately we take this spacing goes to 0, and also the volume of the box is thermodynamically large to relate with the physical world. So this is our setup. This is a 3-dimensional box, and these black dots are our lattice points, and these red lines which you see, these are the gauge links which connects the two different lattice sites. And the volume of the box is defined as n cube times a cube, where n is the number of lattice point along the spatial direction. And in the lattice unit, you can write temperature as 1 by n tau times a, where n tau is the number of lattice point along this temporal direction. And the volume of the box in our simulations are fixed to be around, in the one direction is fixed around 4 femtometer. This is the requirement to achieve the thermodynamic limit. And while generating the configurations, we fix the mass of up and down quarks to be roughly around 5 MeV, and the mass of strange quarks to be around 100 MeV. These are the physical masses. So next, when is the UA1 effectively restored? Since the flavored singlet part of the chiral symmetry is anomalous, it has any corresponding order parameter. So in order to study this problem, it was suggested by Suryak to look at the degeneracies of the integrated two-point correlation of mesons, which are chi pi minus chi delta. So from this picture, you can see that this pi under UA1 restoration, pi and delta are the degenerate states. Similarly, sigma and eta are also the degenerate states. So when these correlators will become degenerate, eventually you would expect that the value of chi pi minus chi delta will go to 0. And that's why what we try to calculate in the terms of the eigenvalues of the Dirac operator. So over here, we have calculated the value of chi pi minus chi delta for 3 different lattice spacing for the 4 different temperatures. All are above Tc. And finally, we have taken its continuum limit. So y-intercepts are the value of chi pi minus chi delta for the different temperatures in the continuum limit. So one thing you can observe from here, that as the temperature increases, the different color represents the different temperature. So basically, as the temperature increases, the value of chi pi minus chi delta decreases. So eventually you will expect that at some higher temperature, the value of this chi pi minus chi delta should go to 0. So that's what we try to figure it out over here. So these are the value of chi pi minus chi delta for all the 4 different temperatures in the earlier slide. And next we do a 1 by T square functional fit, which is, this is a motivation coming from this chiral perturbation theory. And we try to figure it out what is the temperature where this value of this chi pi minus chi delta goes to 0. And we estimated that the temperature is roughly around 1.14 Tc, where this after that the UA1 will get restored. So the summary of the talk. So by carefully performing a continuum extrapolation, we show that UA1 remains effectively broken in the chiral symmetric phase of QCD below temperature 1.15 Tc. But I didn't tell you that why this is happening. So over here, this is a plot of the histogram plot of the eigenvalues of the Dirac operator. So here you can see the 2 differences. Below Tc, this 145 MeV is the below Tc temperature. So and all are the above Tcs. So above Tc, you see that there is a peak-like a structure over here, and the linearly rising part, which we call as bulk modes. So, but there is no any peak-like a structure below Tc. Earlier, in the chi pi minus chi delta calculation, I didn't mention that the maximum contribution, in fact 99% contribution, is coming from this near 0 mode peak part only. So this peak part is basically the reason behind the finite value of this chi pi minus chi delta. So from here also you can see that as the temperature increases, the peak height is decreasing. So when the peak will be gone, so 99% contribution will also be gone. So the value should go to 0, roughly go to 0. And this near 0 peak part is also linked with these instantons, which are the topological object, and those instantons are basically the zero energy and finite action solution for the gauge field. So next, at temperature less than Tc, the interaction between the instantons are strong, hence the near 0 modes have quite significant overlap with the bulk modes. That's why we don't see any peak-like structure over here. And at temperature greater than Tc, the strength of interaction between the instantons starts to weaken. Instanton tunneling probability also decreases, resulting in the lowering of the height and the width of the near 0 peak. And interplay of both these leads to a separation of this near 0 and peak out of the bulk modes, which also happens to be around 1.15 Tc. This is another calculation we did in our work. I didn't mention it over here. So, and how different topological, there are many topological objects in QCD, dions, vortices. So how these different topological object plays a role in this phenomena needs to be further investigated. That's all. Thank you.
So we have time for a couple of questions. The back.
So you mentioned like extrapolating the data. So how you extrapolate the eigenvalue spectrum? I mean, what are the finite size effects, or like how?
No,
you
we
go
didn't
to
extrapolate this eigenvalues plot. These are for the different temperatures coming from the simulations only.
So how you go to continuum in numerically? I mean, you mentioned.
We don't take the continuum limit of this spectrum. We calculate some observable by using these, and after that we take the continuum limit. In the continuum limit, basically you can see from here that this is for the much finer lattice. This is for the 64 cube times 16. So in continuum also, roughly you will expect that the eigenvalue spectrum should look roughly the same, like this only. Oh, that has already been taken care of. I have put some cut. That is not present over here. That already removed.
Yeah.
Yeah.
How does Higgs mechanism of mass generation for quarks interfere with this scenario?
No idea.
Because finally Higgs is supposed to give some mass to every particle, including quarks. So it should be interfering with the chiral symmetry break. Anyway, we can discuss it.
No, this happens at very high speeds.
So that's what. So is there a natural separation?
Yes, yes. The electroweak scale is much higher than the QCD scale.